Safe return, the art and science of astronaut reentry. Space exploration represents one of humanity's greatest achievements, pushing the boundaries of science and technology to uncover the mysteries of the universe. While launching astronauts into space is an incredible feat, ensuring their safe return to Earth is equally critical. The journey back to our planet involves intricate planning, cutting-edge technology, and precise execution to protect both the crew and the spacecraft. Understanding how astronauts return to Earth offers a fascinating glimpse into the challenges of human spaceflight and the ingenious solutions developed to overcome them. In this article, we'll explore the step-by-step process that ensures astronauts land safely, the technology behind re-entry systems, and the future innovations shaping this critical aspect of space exploration. As astronauts conclude their mission in space, careful preparations are crucial to ensure a safe and successful return to Earth. These preparations involve both precise maneuvers of the spacecraft and thorough safety measures for the crew. Before re-entry, the spacecraft must transition from its orbital path to a trajectory that will bring it back to Earth. Deorbit burns. The spacecraft performs a deorbit burn by firing its thrusters or engines in the opposite direction of its travel. This action reduces the spacecraft's velocity, causing it to descend from orbit. The timing and duration of the burn are meticulously calculated to position the spacecraft on the correct re-entry path. Trajectory adjustments. Mission control teams calculate the optimal re-entry angle and trajectory to ensure the spacecraft enters the Earth's atmosphere safely. An angle that is too steep can lead to excessive heating and structural stress, while an angle that is too shallow may cause the spacecraft to skip off the atmosphere back into space. Safety protocols are implemented to protect both the crew and onboard equipment during the intense conditions of re-entry. Crew safety measures. Astronauts don their spacesuits or re-entry suits, which provide protection in case of cabin depressurization and help regulate body temperature. They strap into specially designed seats with harnesses that help distribute the forces experienced during re-entry, reducing the risk of injury from high G-forces. Stowing equipment. All loose items within the spacecraft are securely stowed to prevent them from becoming dangerous projectiles due to the gravitational forces and turbulence of re-entry. Sensitive equipment is safeguarded, and experiments are properly stored to preserve any collected data. System checks. The crew conducts final checks on all essential systems, including life support, navigation, and communication systems. Backup systems are prepared in case of primary system failures during re-entry. Atmospheric re-entry is one of the most critical and intense phases of an astronaut's journey back to Earth. During this stage, the spacecraft transitions from the vacuum of space into the dense layers of Earth's atmosphere, encountering extreme heat, pressure, and deceleration forces. Precision engineering and advanced materials are vital to ensure the spacecraft and its occupants survive this demanding process. The trajectory for atmospheric re-entry is carefully planned to balance safety and efficiency. Re-entry angle. The angle at which the spacecraft enters the atmosphere is critical. A steep angle can lead to dangerously high temperatures and structural stress, while a shallow angle might cause the spacecraft to skip off the atmosphere like a stone on water, delaying or preventing re-entry. Controlled descent. The spacecraft follows a predetermined path to guide it through the atmosphere. Minor adjustments may be made during the descent to maintain the correct trajectory. Re-entry generates intense heat as the spacecraft compresses and ionizes the air molecules in its path, creating a fiery plasma. Heat shields. The spacecraft is equipped with a specially designed heat shield to protect it from the searing temperatures, which can exceed 3,000 degrees Fahrenheit, 1,650 degrees Celsius. These shields are made from materials that either ablate, burn away, carrying heat with them, or reflect heat to minimize damage to the spacecraft. Thermal management. Modern heat shields often use reusable materials, like those found in SpaceX's Dragon capsules, which reduce costs and enhance the sustainability of space missions. As the spacecraft rapidly decelerates during re-entry, astronauts experience intense G-forces, often several times Earth's gravity. Physical effects. These forces can make it difficult for astronauts to move or breathe, putting significant strain on their bodies. Proper training and positioning within specially designed seats help mitigate these effects. Protective measures. Spacecraft interiors are equipped with shock-absorbing materials, and astronauts are positioned to minimize stress on their spines and internal organs during this phase. As the spacecraft descends, the surrounding plasma can block radio signals, causing a temporary communication blackout. Duration. This blackout typically lasts a few minutes, during which mission control relies on pre-programmed systems and onboard automation to ensure the spacecraft follows its intended path. Resumption of contact. As the spacecraft slows and descends into denser atmospheric layers, communication is restored, allowing mission control to guide the final stages of re-entry. Atmospheric re-entry is a testament to the engineering and precision required in modern space exploration. From withstanding immense heat to enduring G-forces, every element is designed to ensure the safety of the astronauts and the success of the mission. This phase transitions seamlessly into the descent and landing process, bringing the astronauts closer to home. Astronaut return, descent, landing, and recovery. The descent and landing phase is the final stage of an astronaut's return journey to Earth. During this phase, the spacecraft transitions from the intense heat of atmospheric re-entry to a controlled landing at a predetermined location. Precision, coordination, and advanced technology are key to ensuring the safety of the crew and spacecraft. A. Parachute deployment. Parachutes play a critical role in slowing down the spacecraft during the final stages of descent. Sequence of deployment. Drogue parachutes. These small parachutes are deployed first to stabilize the spacecraft and reduce its speed significantly. Main parachutes. Once stabilized, larger parachutes deploy to further decelerate the spacecraft, bringing it to a safe landing speed. Timing and automation. Parachute deployment is carefully timed and often automated to ensure proper functioning at the right altitude and velocity. B. Landing zones. The choice of landing zone is crucial for a safe recovery. Water splashdowns. Traditionally, spacecraft like the Apollo capsules landed in the ocean. Water landings provide a softer impact, but require specialized recovery teams and equipment, such as helicopters and ships. Land-based landings. Modern spacecraft, like Russia's Soyuz and SpaceX's Dragon, are designed to land on solid ground. These landings often utilize additional systems, such as airbags or retrorockets, to cushion the impact. Pre-selected sites. Landing zones are carefully chosen based on weather, accessibility for recovery teams, and safety considerations. C. Retrorockets and airbags. Some spacecraft are equipped with additional systems to ensure a softer landing. Retrorockets. Small rockets are fired just before landing to slow the spacecraft's descent further, reducing the impact on the ground. Airbags. Inflatable systems deploy around the spacecraft to absorb the shock of landing, protecting both the crew and equipment. D. Recovery operations. Once the spacecraft has landed, recovery teams spring into action. Search and rescue teams. Ground or naval crews locate the spacecraft, which often transmits signals to aid in tracking. Recovery teams approach cautiously to ensure the area is safe before accessing the crew. Crew extraction. Specialized tools and trained personnel extract astronauts from the spacecraft, often requiring careful handling to avoid further stress on the crew after their journey. Transport to medical facilities. Astronauts are taken to nearby medical facilities for immediate checkups and care to assess their physical condition after exposure to microgravity and re-entry forces. Descent and landing mark the culmination of months or years of mission planning and execution. Each step, from parachute deployment to recovery, is meticulously designed to ensure that astronauts return home safely, ready to share their experiences and insights from space. This phase not only signifies the success of the mission, but also serves as a stepping stone for future endeavors in space exploration. Recovery operations are the final critical step in ensuring astronauts' safe return to Earth after their mission. These operations involve retrieving the spacecraft, securing the crew, and conducting immediate health evaluations. Precision planning and rapid execution by recovery teams are essential to successfully complete the mission and transition astronauts back to life on Earth. A. Search and rescue teams. Once the spacecraft has landed, specialized search and rescue teams are deployed to locate and secure it. Tracking and location. The spacecraft transmits beacon signals to aid recovery teams in pinpointing its landing site. GPS systems and communication equipment play a crucial role in locating the spacecraft quickly, especially if it lands off course due to weather or other factors. Approach protocols. Teams approach cautiously to assess the spacecraft's condition and ensure no hazards, such as fuel leaks or structural damage, pose risks to the crew or recovery personnel. B. Crew extraction. The process of safely extracting astronauts from the spacecraft is carefully planned and executed. Opening the hatch. Recovery personnel open the spacecraft hatch, often requiring specialized tools due to the tight seals and potential heat from re-entry. Assisting astronauts. Astronauts, weakened by prolonged exposure to microgravity, may require assistance exiting the spacecraft. Recovery teams are trained to handle them with care, minimizing strain on their bodies. Initial assessments. Quick health evaluations are conducted on-site to check for signs of dehydration, disorientation, or other immediate health concerns. C. Medical checkups. Post-landing medical evaluations are crucial for assessing the astronaut's physical condition after their time in space. Microgravity effects. Prolonged exposure to microgravity can lead to muscle atrophy, bone density loss, and cardiovascular changes. Medical teams evaluate these conditions and begin initial treatments if necessary. Reacclimatization. Astronauts often experience dizziness, fatigue, and difficulty walking as their bodies readjust to Earth's gravity. Recovery protocols include support for standing and mobility. D. Transport and debriefing. Once initial recovery steps are complete, astronauts and the spacecraft are transported to secure facilities. Astronaut transport. Crews are flown or driven to nearby medical facilities or mission control centers for in-depth evaluations and debriefing. Spacecraft retrieval. The spacecraft is transported to research facilities for inspection, data collection, and analysis of re-entry performance. E. Psychological support. The mental health of astronauts is a priority during recovery. Debriefing sessions. Astronauts discuss their experiences, both technical and personal, to help scientists and engineers improve future missions. Emotional adjustment. Returning to Earth after weeks or months in space can be overwhelming. Psychological support is provided to help astronauts reacclimate to normal life and address any post-mission stress. The process of returning astronauts to Earth is a testament to human ingenuity, precision engineering, and meticulous planning. From the initial preparations for re-entry to the intense phases of atmospheric descent, landing, and recovery, every step is designed with one goal in mind: ensuring the safety of the crew and the success of the mission. Re-entry is one of the most challenging aspects of space travel, requiring spacecraft to endure extreme conditions, including high temperatures, G-forces, and rapid deceleration. Innovations such as advanced heat shields, parachute systems, and retro-rockets have made this process safer and more efficient, allowing modern spacecraft to reliably bring astronauts back to Earth. Equally critical are the recovery operations that ensure astronauts receive immediate medical care and a smooth transition back to life on Earth. These steps not only protect their physical health, but also gather valuable data to improve future missions.